All right. Thanks a lot. I hope everybody's connected, and it's a pleasure to be here remotely from Italy. So sun is shining and everything is doing well. So I work for Trend Micro Research. So this is a team of researchers within Trend Micro that focus on new threats and designing potential solution to such issues. And we've been working in the domain of radio protocol securities over the last, I would say, 5 years, pretty much right now. So this presentation I'm going to give you here is a kind of summary of what we found in the wild and a bit of status of this area of research, which has been probably not overlooked as other area of research like web security or malware, for example. So this is not a work that I did entirely by myself. It's a joint effort between myself and colleagues within Trend, as well as independent researchers that have helped us along these years. So let me start by this Latin quote that said that basically, if you are unaware of something, that's not an excuse. So it's a bit like you're driving your car, you drink a few beers and you get caught by police. And you might say, okay, I was not aware that in whatever, like in Italy, the limit is 0.5, for a drink and driving. If you're not aware, that's your problem, right? So if you're not aware that there might be bad guys that can attack your system, then it's up to you, it's your problem. So there is no excuse to ignorancia, as we say in Latin. So we start here because we go back to what I call an hardware epoch. So when we talk of radio communication or radio protocols, we have to think of devices like this one you can see on the screen. So this is a photo taken from an ham radio, an ham amateur radio aficionado. And you can see that all these devices, they are very much hardware based. So this is because back in the days, all the communication were made in hardware. So when you want to communicate with someone, you go with this big hardware piece. So you can imagine our old computers, they were basically big computer with big screen. And the consequence of this hardware epoch is that there are actually few important discussions here. So the first is that when you were developing such devices, you were not really thinking that someone would come and attack your device, because these devices are standalone system. They are not connected to the internet. They run by themselves, so they are not exposed, to potential attackers. On top of that, you are not thinking that someone might come and start basically bothering you, so transmitting protocols to you, because there was no easy way for an attacker to develop a radio that could basically connect to your device, because developing radio at the time was very much expensive, because in developing a radio, you had to do it via hardware. So every time, if you are like an attacker, you want to attack someone, you have to develop your own radio. So imagine every time there is a different protocol, you have to develop a different radio, so different hardware pieces. So hacking was very difficult and cost expensive. So as a result of that, developers at the time they were developing this radio equipment, they were embedded, they were using this security through obscurity, they were relying on this security through obscurity paradigm, in which basically they were saying, okay, we are not disclosing information on how the device is done, how the protocol is implemented, and so we are safe. On top of that, this device often came with very low computational power, so there was not really much an option to add encryption or any sort of complexity on top of clear text protocols. Yes, that was actually a big problem, but things get very much worse when a few years ago, security researchers start to use what actually is a software-defined radio. So these are devices that allow you to develop a radio via software. So it's very much a device that you connect via USB to your computer. And then with your computer, you can basically develop any any attacking tool you want. This has the implication of reducing the cost of an attack, so making the attack very much accessible to anyone, reducing the complexity, because one thing is designing an attack tool in hardware, one thing is to design an attack tool in software, no? And on top of that, there is also an increased flexibility, because the board you can see here, for example, which is a board developed by Ethos Research, which is a spin-off of Texas Instruments, very famous brand, is a board that allows you to change, by changing the board here on the top, which is the data board, you can basically adapt the board to a bunch of different frequencies. So you can go from low frequency to high frequency. So it makes basically this system usable in pretty much any condition you want, which is great, no? And there are actually more than just one software-defined radio, because this is a full category of devices. So there are a few that are very cheap, and you can bring with you anywhere you want. You can do reconnaissance, so you can start scanning, for example, frequency over here and see, you know, if there are any potential victims around. One of these is this one you have on the screen, is called RTRSDR. It costs 25 euros and can go from 500 kilohertz to 1.7 gigahertz. And you can basically receive any signal transmitting this radio spectrum, which is pretty well for the first, you know, investigation of what's going on. But of course, things change a bit when you start using software-defined radios that have possibility to transmit as well. So they have a bidirectional transmission. For example, this one, it's called the Yardstick one. It costs a bit more, 150 euros, but with this one, you can basically transmit. So at that point, you, as a bad guy, you can do attack like spoofing. So you can generate, for example, a fake signal. You can do man-in-the-middle attack, for example, by changing an original radio packet, for example. So you can do all the nasty things. But even worse, if you buy something like this, which is developed by some friends from US running a company called Nuanda. So this board, which is pretty much similar to that one I showed you a few slides ago of Texas Instruments, allow you basically to do everything. So you can receive traffic and transmit traffic at the same time. It has a lot of cool features for automatic gain control and offset correction, which in simple word means that you can very easily generate a reliable signal. So you can very easily attack devices that are maybe located even kilometers far from where you are. So yes, so we have seen that over the last 10 years, I would say, these software-defined radios that were mainly used in by radio, telco engineers in labs. This SDR have been made available to security researchers worldwide. So it's very easy to go online and buy all these devices, in a legitimate way. So at that point, you have a device like this one that you have on the left side of the screen, which is one of the devices we will see later on in the presentation. Is a transponder, so it's a sort of radar. And then you have the attacker here on the right now with his own laptop and the SDR connected via USB port to the laptop. So yeah, what could go wrong? Eh? So the talk here today for the rest of my presentation will be on a few examples of what went wrong today and what we could do to raise awareness in this domain, which is underlooked, in my opinion, when compared to other domain of research. So let me start with the first case, which is the automated identification system. So this is a protocol that has been introduced 20 years ago. Actually, is a standard, and is a mandatory of mandatory use for all the passenger ships. As well, ships that have more than 300 tons. And this makes an overall estimation of 300,000 ships worldwide that use AIS for communication, for tracking, for avoiding collision, and so on and so forth. So the device works as in a way similar to how a GPS radar works. So this device that you have here on screen, it basically positions itself via GPS, so it has a GPS antenna on its own, and then it communicates via radio frequency to all the nearby ships and all the, for example, traffic control tower on offshore or the stations that are installed on offshore. They communicate basically the position of a ship. This is how the system works. And yeah, so when we start to look at the spec of the protocol, we noticed that there were no really much mention of things like authentication. So there is no actually mention of how you could, as a ship, authenticate yourself, so prove that you are the real ship in communication. There was no mention of integrity. So it looks like you could potentially change, if you intercept like one of these packets, you could potentially change such packet. So we say, okay, let's take a big look into that. So we bought an S transceiver, this one here in the middle of the screen, this one black with the blue and yellow, blue and white cross here. And we start playing around with such a transceiver. So we developed a radio that was able to talk AES by using the specification. And for that, we use a very standard framework that you want to learn if you want to do research in this area of research, which is called a GNU radio. And with GNU radio, you can easily develop any software radio you want, both for transmitting and both for receiving. And, you know, we did a first transmission to see if we were able to transmit faked ship information. And it turned out that, as you can see on the screen, we were able to transmit a ship called as Trend Micro that was actually moving at 10 knots of speed at 100 degrees course, pretty much horizontally to the right. So the transponder was reading information about all the other ships nearby, as well as our fake ship. So this is already pretty severe, no? Because if you think that this information are used when there are accidents to know where a ship was, if it was the right ship that made an accident, if someone was, for example, fishing in an area where it's not supposed to fish, and you can see who's going to fish there. So if you can fake all this information, then, you know, any incident response activity doesn't make any sense, right? Because all the data can be faked. So we are able to fake such ship. Most interesting, we are basically located here, close to the pole, and we are transmitting our signal from the room of the hotel. And we had basically one of the AES tower installed on the shore that was basically collecting as well our signal and upstream such information over the cloud. So all the cloud providers like this one you have here on screen that tell you the position of the ships globally in real time had basically our ship, our fake ship information inject in the data stream. And of course, you can, of course, fake things like ship, but you can also fake information that you would not be able to fake if you are not a control tower. What does it mean? It means if you buy one of these AES transponder and install it on your ship, then this AES transponder will broadcast information on where the ship is located, but the transponder is not able to transmit like a control information, like messages that that are normally used by the control tower, no? And so here the idea is that if you can fake things, then you can fake whatever you want, no? So we are able, for example, to fake what is called the closest point of approach alert. And this one would basically allow you to trigger a collision warning and possibly alter a course of a ship, because all the ships are basically using GPS to move along. But if you can basically fake an information like, hey, look, there is a wreck close to you, so you're going to crash on a wreck, you are going to crash on a rock, for example. No, at that point, the ship will react, will raise an alert, saying, you know, warning, I'm going to crash on a rock, and the ship will try to move away. So if you can fake such information of an hazard, like on a rock, for example, then things can get very bad. So let's see an example of this. So let me go here a sec. Let me run this, closest point of approach here. Perfect. So here you will see this is the target bot we're trying to target. This is the proximity alarm that is installed on the bot. So you can see here that's the transponder and that's a siren with light. And this one basically will get triggered if you trigger like a problem of a proximity alarm. And here what I'm going to show you is first we construct a fake bot. That is located at certain latitude and is has such name that you can see on screen. And this is basically how the fake bot gets rendered on the radar of the target ship. Now what I'm going to show you is how we can make such fake bot moving in the direction of a targeted ship. So basically at that point, the target ship will arise an alert because it can see that there is a boat that is actually potentially crashing into the target ship. Of course, this is fake, but if you can generate such fake signal, you can you can create alert, you can make a ship taking a different direction and possible crash into something. And even worse, you can also create messages that might trigger a denial of service. For example, you can create a message that will ask to a victim to change the operating frequency. So if I'm targeting a vessel or even more than one vessel, for example, all the vessel in a certain area of the sea space, for example, I can say 30 kilometers because I have a reach of 40 kilometers. I can say, okay, instead of using the normal frequency for transmitting, you are now asked to use a different frequency. So at that point, all these transponders will switch to a different frequency and they won't be able to never transmit and never receive any longer on the correct frequency. So it's a pure denial of service attack against all the AES protocol. Here I have an example for this as well. So let me going to show you this. We call it frequency hopping because you hop from the real frequency to the wrong one. So we first, so here we have again the victim on the left side of the screen with an alarm. And here on the top right, we have the attack console. So first we send the same message we sent before to trigger basically an alert as a confirmation that the message was received correctly from the victim. And here you can see that the victim received our fake message. Then we impersonate the port authority and we instruct the receiver to listen on another channel. So here you can see that we specify the two channels to listen to that are different from the original one. At that point, you can see that the victim has completely received and decoded the message that we were able to spoof. At that point, we send again the alert message and we see what's going on here. So at that point, no message is being received and no alarm has been triggered, showing that we managed to do a denial of service attack against one transponder. Of course, you could target one transponder only by specifying its destination in what's called MMSI, but it's VID, or a full region basically of a sea space. Of course, you might say, okay, these are pure theoretical things. Yeah, well, maybe when we were the first to find those problems, they might be theoretical only, but things have changed a lot rapidly over the last few years. For example, this is a report that has been released publicly on June 19th, so a few months ago, where you could see that basically there were two ships here located in Odessa, close to Ukraine. But apparently marine traffic, which is one of those provider side that basically report information, all the ships are located globally, report that some ships were traveling from Odessa down to a Russian naval base in Crimea. So you can see here the path of the ships and where the ships move from one harbor to the other. But actually, if we compare the timestamp in which they were supposed to be moved to the photo from the webcam at 2 a.m., 5 a.m., at 2 p.m., we actually saw, we can actually see that the ships did not move. So, you know, the webcam shows that the ship were always on the harbor, so they didn't move. So this shows that basically false AIS track data were injected into the system, probably with the same attack we have shown you before, where we were able to inject data into this AIS tower located on shore. Of course, this caused a big problem because, you know, you can have, for example, inject the ship into a sea space where the ship is not allowed to be, for example, or creating a problem. I'm not saying a war, but, you know, a problem of conflict between, for example, different adversarial countries, no? And so on and so forth. So this is about AIS, but now let's look into remote controller for the industries. So these are devices like joysticks that are used to control industrial equipment. So industrial equipment can be crane used in construction site, can be containers that are moved in a port, for example, in logistics, can be like industrial robots. So any kind of industrial equipment you might want to think at, basically could be controlled by such devices. So you have basically a receiver, which is this gentleman here on the right side. Actually, it's also on the right, on the left and on the right. So this square box is basically the device. You connect the device to the device you want to control. And then you have a joystick. With the joystick, you can, there are joysticks where, like, you know, like on PlayStation, where with the jog, that basically you can move around things. Or the joystick like this one, where you can lift up, down, move left, right, move clockwise side or anti-clockwise side, and so on and so forth. So basically, you can turn an industrial equipment into a radio remote controller industrial equipment. So what we did, we buy some of these devices. So I guess we bought devices from 8 different vendors to make basically the work more vendor agnostic as possible. Not to finger point against a specific vendor, but to find basically a potential bug in this type of technology. And we did what we called blind reverse engineering of a signal. Because in this specific case, we did not have the protocol specification because everything was proprietary. So this type of device, they were relying on the security through obscurity paradigm. And at that point, there were no specifications to look at. So we started doing some signal analysis like this one, trying to guess which type of encoding the signal we're using, and so on and so forth. But things were not as easy as they were due because there was a lack of information. So by only looking at the signal, analyzing the signal itself was not enough. So we had to go a bit deeper. And in particular, we had to tamper on the bus that connect the MCU, which is a microcontroller, to the radio chipset, to know wherever the MCU was setting some register on the radio chipset and which register. So to that, we use a logic analyzer, which is a tool to basically do this data acquisition on hardware buses. And we had to write basically what we call a SPI emulator to emulate all this communication. At the end, we were able to gather information on which kind of modulation schema were used, how long was the bit length, and so on and so forth. And we were able basically to develop our own software radio. So now in the next video, I'm going to show you what we were able to do. And I'm already anticipating to you that we are able basically to move cranes in a real-world installation with a big impact on safety. So let me go here. So this video is a bit longer than the previous one. So this is the device, one of the devices we analyzed, one of the 8 different vendors. This is one of the software-defined radio we use for the attacks. That's the original transmitter. So as first, we start doing some radio capture to do all this signal analysis I was mentioning to you before. This is one of our other vendor we test. And as a first test, we start basically recording traffic to try what's called the reply attack. So you record the traffic and you reply the traffic to see if you can trigger the same action of the recorded signal. So we start moving, we connect basically in our lab the radio controller to this toy crane to start, doing some tests in-house as first. And then we did the reply attack. So here you can see that the computer is by itself generating a signal using the software-defined radio, and the toy crane is moving and potentially crashing into a human, for example, or anything. So at that point we say, okay, but can we really move a real crane, on a real installation? So for that, we travel to a site, and you can see here that's myself with a legitimate jog. I'm basically talking with one of the operator and not touching the jog, but what happens is that, as you can see down here, we'll be able to move the crane without anyone basically touching the jog, see? Of course, the problem is not only specific to this vendor or to this configuration, but as you can see in this example here, we are also able to trigger vulnerability in auto crane, so a crane installed on such a big track. As well as here in an industrial facility. Here we are generating the signal. You can see the signal get generated correctly on this frequency, 433 megahertz. And here you will see basically that the auto crane, the overhead crane, sorry, will be moving left. Of course, you can move anything you want, basically. So this shows a lack of basic standard security features in all the 7 vendors that we test that turn out to be all remote attackable. So let's now look at fobs. So these one are key fobs and door openers. So they come in different flavor, different color, like red button, blue button, orange, whatever, but they all suffer from similar problems. So let me start by saying that this type of research has been looked already by a bunch of other different researchers. So I suggest you to take a look at this nice video from our friends at Ec5, where they show how by using this portable SDR, which is super cool because you don't even need a laptop. So you have basically an SDR with his own display, everything in all one piece of gadget. And you can basically do simple record reply attacks. So you can record, for example, the key fob and then reply what the signal to see if you can still opening, a car. So here the things is when we start basically putting on the market these key fobs or this controller, basically this opener, like in the 80s, they basically said, okay, do you know what? Everything I want to open, like every car, should have a different code. So the security is basically a function of that. So if you know like the code, you open the car. If you don't know the code, you don't open the car. Yeah, okay, that's very easy, but because even if I don't know the code, I can, as I said, you can record you while you open your car, then you go eating a sandwich in the restaurant, and meanwhile I can reply the signal and I can still open your car, so I can steal your car. So a few years after, they came out with the idea of having as well what's called a rolling code as a part of a message. So both the fob, which is the transmitter, and the car, which is the receiver, use basically a rolling code as a seed for a function that is used to compute the message for opening or closing the car. So every time you press a button, you're basically send a different message to your car, but the car know that the message is correct because it computes basically the algorithm by using the same seed, and can either open the car or not open the car. So here things get a bit more complicated, because if you as an attacker, you capture one of such packet and you record and you reply that, you won't be able basically this packet to open the car, because the message is basically when you press the first time, the car receives such message and then get unvalidated. So if you send again the same message, the message was invalidated, so the message won't open the car. So for that, attackers develop what's called a role jam. So this is a tool that basically use targeted jamming on the message sent by the attacker, by the legitimate user, to be able to basically jam and make sure that the car is not receiving the signal, and then you're going to reply that. It's a bit more sophisticated than that. Here is how it gets described. I'm not going into detail for a lack of time, but basically this device overcome the limitation of this new technique. And finally, basically, people realize that if you use a timestamp, then you are secure enough, because at that point, even if you do a role jam, but the timestamp is wrong, then at that point, the packet gets discarded. The problem here is that if these sort of systems that are not connected to the internet, so they cannot rely on something like NTP, the network time protocol, for keeping an update on the time. This sort of system have really a problem with this last solution, because what about if you change the battery of your key fob, right? You lose basically your time on the fob. At that point, nothing will work anymore. But what I want to show you is that the fact that there were researchers doing research with this area of research has helped improving the final results. So it's basically a history of learning from errors. So you learn from the errors and you get better. So that's why our role as security researcher is fundamental to improve the current ecosystem. That's an intro to my last part of the talk. In the last 5 minutes, I want to tell you how important is what we do. So our goal, endly, is to raise awareness in this domain. So the people that develop radio protocols are aware of the risk that nowadays there are. So you cannot omit the fact that there might be an attacker that can attack your device. Then we want to share our knowledge. So I'm not saying that I'm an expert, because there are tons of people that are more expert than myself, but we did some work in this domain. So we are happy to share what we have learned with new people, and endly to grow a community of radio hackers and radio enthusiasts. So for that need, a few years ago, in particular, I think 4 years ago, we came up with the idea of this, what we call a capture of a signal. So this is a radio-based CTF. So if you ever played a CTF, like for example, DEFCON CTF, or many, you know what I'm talking about. So basically it's a contest where you try to capture a flag. So you have to reverse engineer a system or get into a system to steal a flag to get some points. So you have an idea similar. So you have to reverse engineer a signal, as we did with the radio controllers, to be able to get the points and win the game. So what this activity is called blind signal analysis, because you don't have a specification. It's not super easy, but it basically puts you in a condition to learn new things. And we ran this contest at conference because we wanted to be connected with the community. So we start in 2018 by running it at PAXEC in Tokyo and Hacking the Box Dubai, because we have both connection with the organizer of these two conferences. And things went pretty well, so the people were pretty happy. So we decided on the year after, so 2019, to replicate, and we had Consequest Vancouver and Hacking the Box Amsterdam as additional venues. And we ran this capture the signal 4 times in 2019. And in one of these contests, that one in Amsterdam, we also had an hybrid solution in which we had also signals that were transmitted both in radio at the conference as well as over IP. So we had people that were participating remotely from home, right? And that was very much helpful to set the base for capture the signal virtual that we ran over the last 2 years due to the pandemic. For example, here is a screenshot of a scoreboard that we were using at the last event a few months ago at Hardware.io, where we had about 200 teams playing and competing amongst each other. And we have, of course, winners. So we are giving different prizes for winners. We even had an award ceremony. And this is a lot of fun. So you are actually competing, but people were super happy. So there are people saying, okay, I really enjoyed what you guys have done. It's a lot of fun. So that for us, it's very inspiring because it drives our motivation in doing even better, you know, and providing new things on this in this area of research. We try to adopt an open spirit. So everything we did in the past in our research, or even the research I show you in this talk on AES, on the industrial radio protocol, they are public. And even this capture the signal initiative is public. So you can go over GitHub and download both the tool you can use to reverse engineer the signal, as well as the framework that we released during Black Hat Arsenal US this year. And it's a framework that allows you to run the contest on your side. So we would like that, you know, the community itself will take over and start running contests on their own. So we had already universities that have running contests for their students. We have as well as other companies that they want to run their own radio-based CTS. So you just have to go to this website and download the CTS backend, basically repository for running your own contest on your side. So with that, I want to conclude my talk. Thank you all for listening. And if you have any questions, I guess I will have a few more minutes to answer some live Q&A. Or you can still reach me via Twitter if you want, under the nickname of Mbite, and connect with myself and other people that have helped me developing this presentation and all the research we have done in this contest. Thank you a lot. Thanks for listening. I'm open to questions.